that the problem last what we have discussed was the Lagrange multipliers method. And the specification about the Lagrange multipliers method was that here the constant nature is actually equality trap constant. But now we'll proceed further and we'll discuss about multivariable optimization with inequality constant. Now, multivariable optimization with inequality constant means what? What we have done for the equality constant, here the constant type will be inequality. That is the thing. So if you just try to think about that, if we find or if we consider any standard mathematical form of the multivariable optimization with equality constant, then how it will be look like? It will look like that maximize. Okay, just change the color. Maximize function as a function of n variables if you consider x1, x2, xn. Okay, and subject to the constants hi, x1, x2, xn is less than equal to bi, where I is equal to 1 to n. Now, the problem only here is that how do we convert this inequality constant to equality constant? Because we know how to solve a problem with the equality constant. Only thing we need to understand here that how we can convert this inequality constant to equality constant. And we have already done this in the linear programming problem. You have done that when you are considering simplex method. If the inequality constant is there, you always convert inequality constant to equality constant either by adding the slack variable or subtracting the surplus variable or adding the artificial variable, right? You have done those things? Is it okay to you?
Yes, sir.
Now, here the only benefit what we have as we are dealing with the nonlinear programming problem, last time the variable what we have considered, that variable must be a linear variable. But this time when you are considering the nonlinear programming problem, you do not have such restrictions. So if we are going to convert this less than equal to type to equality type, you can always convert by doing like that. Hi, x1, x2, xn, that was the original function. I am adding si square with that. Okay, and is equal to bi. Now I hope you can understand that when I am considering this si square, I have not never mentioned that whether si square will be greater than equal to 0 or less than equal to 0, because automatically this si square is greater than equal to 0, right? Okay to all of you? Okay, and this option why you have? Because we are dealing with non-linear programming problem. Clear to all of you? Is it okay to all of you? Okay. Now, obviously here we can mention that si square is always greater than equal to 0 for I equal to 1 to n. Clear? Now, we'll proceed to think about that what are the necessary conditions and what are the sufficient conditions of the method of solving this kind of inequality constant. And the method what we are going to learn is known as Karus-Kuhn-Tucker conditions, or in short it will be called as KKT conditions. So the method what we are going to learn is known as Karus, as I mentioned to you, Karus-Kuhn-Tucker conditions, or in short, it will be called as KKT condition. So what are the necessary conditions? We know, first of all, we are going to create the Lagrangian function. So the Lagrangian function is what? L, right? X lambda. I'm keeping it like that. And function is f of x1, x2, xn minus lambda 1 into the first constant, that is h1, x1, x2 dot 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 xn, right? Plus s1 square minus b1. This is your first constant. Okay, to all of you? What was the constant? What do you have? The constant what you have is this hix is less than equal to bi. This is the constant what you have. Clear? So when you are going to add this si square, this is going to come like that. You can also convert this as I have done it already for the Lagrange's multipliers method, that you can consider that this as gix less than equal to 0. Also you can do that, where you can consider gix equal to hi x1 x2 xn minus bi. You can also write down this gix. Okay, to all of you? And that means this constant will then move to gi x1 x2 xn plus si square is equal to 0. Is it fine to all of you? Any doubt if you have, please ask me. Is it okay?
Yes, sir.
So that means this constant you can now modify to, as I've written h1, g1, x1, x2, xn minus b1. This can be replaced by g1 then. This can be replaced by g1, x1, x2, xn, right? Plus s1 square. Okay? Minus lambda 2 into g2, x1, x2, xn plus s2 square. Similarly, how many constants do you have? M constants, right? How many constants do you have? Okay, so make it m so that it will be different. M. How many constants do you have? M constants we have, and number of variables we have n. So I can proceed like that up to minus lambda m gm x1 x2 xn plus sm square. Is it okay? Is it okay? Okay. Now, one thing you should remember, that in the Lagrangian function of the equality type constant, we have only two types of variable. One is x and one is lambda. This time we have another variable which is s. So this time the Lagrangian function is depending on three types of variable. One is x. X means basically x1, x2, xn. Lambda basically means s2 up to sn. So now what we have done earlier, we have take the partial derivatives with respect to each of the variable. Then with respect to x, with respect to lambda, with respect to s. So the KKT necessary condition. KKT necessary condition is what? Partial derivatives with respect to, I can say, del xi. Then what we are going to get? Anyone? Del f, del xi minus I can write down in summation I over I equal to 1 to m lambda I. Okay, make it j, then it will be easy for you to distinguish. Lambda j del gi, okay, gj, sorry, del xi. And this is going to be true for I equal to 1 to n, because n variables are there, x1, x2, xn. Any doubt if you have, you please ask me. Is it okay, fine, till now? Okay. Next is what? Partial derivatives with respect to lambda j. Then obviously partial derivative, if you take as this term is free from lambda, this is going to be 0. So what is going to come? For lambda 1, you are going to get this. For lambda 2, you are going to get this. So for lambda j, you are going to get this one minus gj x1 to xn plus sj square. Right or wrong? Is it okay? Similarly, this is going to be true for j equal to 1 to m. And another partial derivative will come because of the another variable s. So del L del Sj is going to be what? Minus 2 lambda j Sj, and this is going to be true for j equal to 1 to m. Additional constant, what you are going to consider here, that lambda I, that should be greater than equal to 0. Okay? For I equal to 1 to m. Sorry, lambda j. Lambda j for j equal to 1. Actually, why it is required here? Anyone? Why this lambda j is greater than equal to 0 for this inequality constant problem? Anyone? Why this lambda j should be restricted? Either positive or negative, that does not matter. But why it is restricted here? Anyone, please? Anyone? No one? Because you can see, yes. Because
So
you can,
because the value is negative, so if lambda j is negative, it will become positive.
no, the logic is that here the type of the constant is inequality type. If you take greater than equal to 0, and if you do not restrict lambda j, then this greater than equal to may change to less than equal to 0 in the Lagrangian function if you do not restrict lambda j. Is it clear now what I'm saying? That to fix this inequality, whether it is greater than equal to 0 or less than equal to 0, you need to restrict this lambda. Clear to you? Is it clear to you? What I'm saying that what we have done, where lambda is used for each of the constant. And because of this constant, if it is less than equal to 0, we are going to add s1 square or add sj square. And if it is less than equal to greater than equal to 0, then we are going to subtract sj square. Now, whether we are going to subtract or add, that is basically depending on greater than equal to 0 or less than equal to 0. This type of constant is given to you. Okay. Now, if we do not fix the nature of lambda, then this greater than equal to 0 and less than equal to 0 will not going to come here. Because if lambda is negative, then this is going to come as negative. If lambda is positive, then this is going to come as positive because of these reasons. So less than equal to type constant is there, or greater than equal to type constant is there, you cannot identify. Okay, what I'm saying? So that is the reason. That's why we need to restrict that lambda. And last time, as it was equality constant for the Lagrange's multipliers method, so that's why it is not required actually, whether it is less than equal to 0 or greater than equal to 0. But because in each of the cases, ultimately it will be remain as equal to 0. Okay now? Is it okay now?
Yes, sir.
Okay. Now the question is that we have find out the necessary condition, and we have seen that in the necessary condition we are going to get the stationary point. Now in the Lagrange multipliers method, we have find out the border Hessian matrix and we have identified the nature. But this time, this method, that KKT conditions, will give you in different way. So what KKT condition gives you as a sufficient condition? It says that, listen very carefully, I'm writing each of that part, and after that we'll discuss this thing. For the standard maximization problem, standard maximization problem, what type of problem is called the standard maximization problem? You have done that in linear programming problem. Anyone? What type of problem will be called a standard maximization problem? When you are dealing with dual problem, I hope you have done that part, right? What is the meaning of standard maximization problem? Anyone? Where the objective function is going to be maximized and the constant are less than equal to type. This type of problem is called a standard maximization problem. Standard minimization problem means the objective function is going to be minimized and the constant are greater than equal to type. Okay to all of you? What type of problem will be called a standard maximization problem? What type of problem will be called a standard minimization problem? Is it okay? Is it okay?
Yes, sir.
Okay. So I'm just writing for you so that you never forget this thing. That for the standard maximization problem, that is in the problem, in which we maximize objective function fx, and subject to the constants gix is less than equal to 0 for I equal to 1 to m. Okay, so this type of problem will be called a standard maximization problem. And one thing also we should mention, that x is greater than equal to 0. Okay, for the standard maximization problem, the KKT conditions, the KKT better say necessary condition, KKT necessary conditions, several conditions are there, are also sufficient condition for the maximization, for the maximum of fx, provided the objective function, provided fx, provided the objective function, provided fx is concave and each constant, that is each gix is convex. X is convex. Please go through the statement again. That I will explain that what is the meaning of this sufficient condition. If you have any query, please you can ask me, because this is the thing what you need to understand before proceed to solve a problem. Because if you do not understand this thing, it will be difficult for you to solve the problem. Please. Please. Is it okay? Is it okay to you? Achha, what is the meaning of that? That equity necessary condition are also sufficient condition. What is the meaning of that? Anyone? Anyone? What's the meaning of that? Am I audible to you? Am I audible to you? So please answer. What is the meaning of that? Equity necessary conditions are also sufficient conditions? Anyone? Equity necessary condition are also sufficient condition means that from the necessary condition, what we are getting the stationary point. From the equity necessary condition, we are getting the stationary point. Now, the stationary point, what we are getting, if it follows this criteria, that objective function is concave and gix is concave, that means each constants are convex, then the point what we are getting from the necessary condition, that is going to maximize the function. That is going to maximize the function. Clear to you what I'm saying? Is it clear to you what I'm saying? Is it okay to you what I'm saying?
Sir, can you repeat once more?
Yes, what I'm saying that from the necessary condition, what we are getting? We are getting the stationary point. Some values of x1, x2, xn, lambda 1, lambda 2, lambda m, and correspondingly, obviously, s1, s2, sm. Now, that stationary point, whether it will maximize the function or not, how do you know? If the objective function is concave and if each of the constant is convex, then we can say that the point what we are getting from the necessary condition, that is actually going to maximize the objective function. Is it clear now? Is it clear now?
Yes, sir.
Now, if I ask you one question, very interesting thing. Suppose that we have applied KKT conditions for a problem where it is for a maximization problem. Suppose that it is not satisfying these conditions. Suppose that the function fx is not concave or the constants are not convex. If such kind of scenario happened, then what do you think? What is going to be happen with the stationary point? What is going to be happen with the stationary point? What is your idea? Acha, what is the meaning of that? The necessary condition will going to maximize the function fx. Initially, what I mentioned that when the objective function is concave and the constants are convex, what is the meaning of that? That means from the necessary condition, you are going to get only one point where you are going to get the maximum. Clear to you what I'm saying? That means when the function fx, objective function fx is concave and each of the constant is convex, then you are going to get only 1 point from the stationary or necessary condition, and that point will going to maximize the function. But if you find out a function, a problem where the objective function is not concave or the constants are not convex, in that case, you are going to get more than one stationary point. And from those stationary points, you have to find out which point gives you the maximum value. Is it okay to you what I'm saying? Is it okay to you?
Yes, sir.
Okay, we are going to understand this again. When you solve the problem, I'll give you the better explanation there, because we don't know even right now because how to solve the problem. When you solve the problem, I hope you get the idea that how to find out or how to know that whether it will give you the multiple stationary point or the single stationary point. Now, the second case, this is talking about the standard maximization problem. Now we are going to talk about the standard minimization problem. So again, the statement will be remain same. I'm not repeating the same. For standard minimization problem, I'm not writing again. So for the standard minimization problem, what is going to be happen? We are going to minimize the objective function and the constants are greater than equal to type. Okay. The KKT necessary conditions are also sufficient condition for the minimum of fx, provided, anyone guess what will be the nature of the function fx, provided fx is, anyone?
Convex.
Very good. Convex. And what will be the objective function? What will be the constant's nature?
Concave.
Exactly. EGIX is concave. Is it okay to all of you now? That for the maximization problem, if it is a standard maximization problem, obviously, first of all, you have to check whether the problem is given in the standard maximization problem form or not. So for the standard maximization problem, the objective function must be a concave function and constant must be a convex function to check that necessary condition is going to be follow the sufficient condition or not. And for the standard minimization problem, the objective function must be convex and each of the constant must be concave. Let's solve a problem. I hope then you better get an idea that what this sufficient condition is talking about. Have you done that? Shall we proceed to solve a problem?
Yes, sir.
Okay. I have first write down the problem. Here we are going to maximize a function with two variables, x1 and x2, which is 10x1 minus x1 square plus 10x2 minus x2 square, and subject to the constants minus x1 plus x2 less than equal to 6, x1 plus x2 less than equal to 14, and x1 x2 greater than equal to 0. First of all, if I ask you, is this problem is a standard maximization problem? Is this problem is a standard maximization problem?
Yes.
Yes, because here we have to maximize the function, objective function, and both the constants are less than equal to type. Now, it may not be happen always. It may happen that one of the constant may be given like that. x1 minus x2 greater than equal to minus 6. It may be given like that also. In this form, this is not a standard maximization problem. So how to convert into the standard maximization problem? We are going to multiply by the minus 1 here. Getting my point or not? Is it okay to you? If it is not a standard maximization problem, we can always convert into a standard maximization problem by transforming greater than equal to sign to less than equal to sign by multiplying the minus 1. Okay, to all of you? Is it okay?
Yes, sir.
So first we are going to mention that the given problem is a standard maximization problem. Standard maximization problem. Now next, if it is a standard maximization problem, what we have to do next? We have to check whether the objective function is a concave function or not. And how to check that? Again, we are going to take the help of the Hessian matrix, and we are going to say that whether it is negative definite or not for all x. If it is negative definite for all x or negative semi-definite for all x, then we can say that it is a concave function. Okay? So first of all, we are going to find out the Hessian matrix. So Hessian matrix is what? Do you remember anything? Partial derivatives with respect to x1, second order. Then it is mixed derivative, del x1, del x2. Then it is del 2f, del x2, del x1. And then it is del 2f, del x2, 2. Only two variables are there. So that's why it is going to come as 2 cross 2 matrix. Okay? Is it okay? What is del 2f, del x1, 2? What is del 2f, del x1, 2? Anyone? Anyone? अरे ये तो कम से कम बोलो. Del 2 of del x1 2, what is that? Minus 2. There is no term with x1, x2. So it is going to be 0. Right? As this one is 0, so this will be also 0. And del 2 of del x2 2 is minus 2. Okay? So next, what you are going to do? H1, first principal minor, H1. H1 is what? Minus 2, which is less than 0. H2 is what? Minus 2 into 2, that is 4. Determinant of H, right? That is 4, which is greater than 0. So what is the nature of the function? What is the nature of the Hessian matrix? H is negative definite, right? H is negative definite. And hence, f is a concave function. F is a concave function. Because it's negative definite for all x. For all x1, x2. That's why it is a concave function. Okay to you? Is it okay to you? Is it okay to you? Is it okay to you?
Yes, sir.
Next, what we are going to check? We are going to check the constants. What is the nature of the constant? Now you can see that both the constants are linear function. And you know, the linear function is considered as both convex as well as concave function. So that's why you can just mention here that g1, which is minus x1 plus x2 minus 6, and g2, which is nothing but x1 plus x2 minus 14. Both are linear function. We can mention that. You need not to show, because linear function are both convex as well as concave. So g2 is x1 plus x2 minus 14 are linear functions. Are linear functions and can be considered as convex function. Can be considered as convex function. Okay. Can be considered as convex function. Is it okay to you? You can mention that it is a linear function, that is enough, because linear function are both convex as well as concave. Is it fine?
Yes, sir.
Okay. So now both the conditions are satisfying here. First of all, we have to check it is a standard maximization problem or not. We have checked that it is a standard maximization problem. Next, we have to show that the objective function is concave and the constants are convex. Both the properties are satisfying. So what we can think about, the necessary condition what we are getting, that is actually going to follow the sufficient condition. Okay. And necessary condition means what? First of all, we are going to create the Lagrangian function. So the Lagrangian function is Lagrangian function is L of how many variables are there? X1, X2, two constants are there. You are going to get lambda 1, lambda 2, and again you are going to get S1, S2 for each of the constant. So actually the Lagrangian function is depending on 6 variables: x1, x2, lambda 1, lambda 2, S1, S2, and the function is what? 10x1, right? क्या था? 10x1, yes, 10x1 minus x1 square plus 10x2 minus x2 square. So 10x1 minus x1 square plus 10x2 minus x2 square. Next, the constant part, minus lambda 1 minus x1 plus x2, okay, plus s1 square minus 6. Am I correct? Is it okay? Lambda 2. What is lambda 2? x1 plus x2 less than equal to 14. So x1 plus x2 plus s2 square minus 14. This is your Lagrangian function. And what we are going to do now? We are going to find out the partial derivative S1, S2, and then we are going to solve those system of linear equation to get the values of x1, x2, lambda 1, lambda 2, S1, S2. Okay to you? So first, partial derivatives with respect to x1. What is going to come? 10 minus 2x1 plus lambda 1 minus lambda 2, which is equal to 0. Partial derivative with respect to x2. What is that? Sorry, which is 10x2. It's going to be what? 10 minus 2x2 minus lambda 1 minus lambda 2 equal to 0. Now next, partial derivative with respect to lambda 1. What is that? Minus of minus x1 plus x2 plus s1 square minus 6 is equal to 0. This is your first constant. Second is partial derivative with respect to lambda 2. What is that? Minus of x1 plus x2 plus s2 square minus 14 is equal to 0. Okay. And next we are going to take the partial derivative with respect to s1 and s2. So partial derivative with respect to s1 is what? Minus 2 lambda 1 s1 is equal to 0. And partial derivative with respect to s2 is what? Minus 2 lambda 2 s2 is equal to 0. So this is your 6 equations. What do you have? Now, as I mentioned to you always, that first of all, you are going to find out the value of x1 and x2 in terms of lambda and lambda 2 from the first two equation. So what will be the value of x1? 10 minus sorry, plus lambda 1 minus lambda 2 divided by 2. Just I multiply by the minus 1 and then I have taken that x1. Okay to you? Is it okay?
Yes, sir.
Similarly, x2 will be what? 10 minus, sorry, plus lambda 1 or minus lambda 1, right? Yes. After multiplying the minus. Minus lambda 1 minus lambda 2 divided by 2. Okay? Now, this equation you cannot evaluate because here s1 square is there. So you can write down this way that this is going to be minus x1 plus x2 plus s1 square minus 6 equal to 0. This is another equation. And this is going to be x1 plus x2 plus s2 square minus 14 equal to 0. This is another equation. Now, from the last two equations or last relation, you cannot find out much because when lambda 1 into s1 is equal to 0, you can say either lambda 1 0 or s1 0 or both can be 0. Similarly, lambda 2 s2, you can say lambda 2 equal to 0 or s2 equal to 0 or both can be 0. Now, how many variables we need to find out? Anyone? How many variables we need to find out? x1, x2, lambda 1, lambda 2, and s1, s2. So how many variables?
6.
6. And how many equations do you have? Effective equation. 1, 2, 3, 4. Right? 1, 2, 3, 4. These 4 relations do you have? But you have to find out 6 variables. Is it possible to find out? Is it possible to find out? So here the problem is that we have less number of equations than the number of variables. And to find those variables, we are going to take the help of the last two relations. Because the last two relations says us that lambda 1 s1 equal to 0 and lambda 2 s2 equal to 0. We are going to omit out of this lambda 1 s1 and lambda 2 s2 any of the two variables. That means as lambda 1 s1 equal to 0, lambda 2 s2 equal to 0, I can consider from the first relation as lambda 1 0 and lambda 2 0. Or I can consider the combination of this lambda 1 0 s2 0. Or I can take the combination of s1 0 lambda 2 0 and s1 0 s2 0. Clear to all of you what I am saying? That I am going to eliminate any one of the any two variables out of the 6 variables. And the elimination can be possible by these two relations only. Clear to all of you what I am saying? Is it okay to all of you? Is it okay?
Yes, sir.
So now the first case. Case 1. I'm assuming that lambda 1 is equal to 0 and lambda 2 is equal to 0. So from the lambda 1 s1 is equal to 0, I'm assuming one relation as lambda 1 0, and from lambda 2 s2 equal to 0, I'm assuming lambda 2 equal to 0. Okay? Now if lambda 1 and lambda 2 equal to 0, then you can see that x1 will be what? 10 by 5. And x2 will be what? Again 10 by 5. That means x1 is 5, x2 is also 5. So for the case 1, as lambda 1 equal to 0, lambda 2 equal to 0, x1 is 5 and x2 is 5. Okay? Now, is this solution is a feasible solution? First of all, you have to identify that. Clear? If this solution is a feasible solution, then it should satisfy all the conditions. And the first condition, what you need to look for, that whether s1 square and s2 square are positive or not. Because if they are negative, is it possible that s1 square and s2 square are negative? कभी पॉसिबल है कि s1 स्क्वायर s2 स्क्वायर नेगेटिव हो जाए? What I'm saying, are you getting? Is it possible to get at S1 square as a negative for the real value?
No.
No. So that's why, first of all, to check the feasibility, we are going to first check whether S1 square and S2 square are positive or not. Because lambda 1 and lambda 2 always already we have assumed that it is equal to 0. So no need to check for lambda 1 and lambda 2. We are going to check only for S1 and S2 or S1 square and S2 square. So relation is what? Minus x1 plus x2 plus s1 square equal to minus 6. So from this, what we are going to get? Minus 5 plus 5 plus s1 square minus 6 is equal to 0, which says that s1 square is equal to 6, which is greater than 0. Next relation is what? x1 plus x2, that is 5 plus 5 plus s2 square minus 14 is equal to 0. That means s2 square is equal to 4, which is greater than 0. So the condition what is required to fulfill, it is satisfying all the conditions. Just go to the problem. X1 and x2 are both greater than equal to 0. It is coming here 5 and 5. S1 square and S2 square, they should always be greater than equal to 0. It is also happening here. And lambda 1, lambda 2 are also greater than equal to 0. It is also assuming here. So the value what we are getting from this case 1, it is actually a feasible solution. Is it okay to you? Is it okay to you? Is it okay?
Yes, sir.
Now, as this one is feasible solution, so this point will give you the maximum of the function. Why? Because the sufficient condition says that the necessary condition is going to follow as a sufficient condition if the nature of the objective function is concave and if the nature of the constant is convex. It is satisfying here. As it is satisfying, so that's why you can say the feasible solution what we are getting. So the feasible solution is basically 5,5. That solution will going to maximize the function. Is it okay? Is it okay? Since the solution does not violate any one of the condition, the solution 5,5, that is your stationary point, gives the maximum of the function f. Maximum of the function f. Of the objective function actually. Of fx, or f you can say. Or f of x1, x2. So now, if I ask you one question, again, I'm asking the same question what I asked earlier, that if we found that the objective function is not concave and the constants are not convex, then can we stop here? I'm getting my point, what I'm saying to you. Suppose that the problem what we are considering as a standard maximization problem, and suppose the function what is given to you, it is not a concave function. Suppose that. Then can you stop here and can you say it is going to maximize the function?
No.
Please. No. That is the problem what I've tried to mention there, that if the objective function is not concave or the constants are not convex, then in that case you have to consider all the four cases. Case 1, case 2, case 3, case 4, because you may find some other feasible solution also in those four cases. So other four cases will be in what? You have to consider lambda 1 equal to 0. You have to consider S2 equal to 0. Sorry, not S1. Similarly, you have to consider other cases as lambda 2 equal to 0, S1 equal to 0. And last case, you may have to consider S1 equal to 0, S2 equal to 0. You have to consider all the 4 cases. You have to find out the stationary point for each of the 4 cases, and then you have to check what are the functional value you are getting. The maximum of those values will going to give you the optimum value actually. Okay to you what I'm saying? Is it okay to you?
Yes.
So in the next class, we are going to discuss one problem where you are not going to find out the optimal value into the first case. You have to proceed for the third, fourth. We have to see. That's it. If you have any question, you can ask me, please. It's a very, very important topic. Please mention. You have to. I have to mention one thing again. That one question definitely going to ask from this KBT condition. If you have seen the previous year question, also you can see that one question definitely asks from that. So you have to understand the logic, because the question what is going to come you don't know. So you have to understand the logic to solve those problems.